Hello, guys. My name is IBM, and I'm bringing you the last episode of particle physics. Do not forget to leave a comment whenever you find something not clear. I can always try my level best to make it very clear. This is the Cambridge International Education, and this is going to be AS Physics. So this is particle physics, atoms, nuclei, and radiation. I think this is going to be lesson three, and I think this is going to be the last lesson of particle physics. So in the first lesson, we introduced particle physics, and the most significant concept in lesson one was Rutherford alpha particle scattering experiment. In the second lesson, the most significant was isotopes and alpha, beta, and gamma radiations. In lesson three, the most significant concept here is actually fundamental particles. So let's enter into fundamental particles. Let's explore what we mean by fundamental particles. Let's understand what we mean by fundamental particles. So in the earlier times, the atom was considered to be the fundamental particle from which all matter was composed. That is about 2,000 years ago. And scientists used this idea to explain the basic structure of all elements. Not until the mid-19th century when scientists such as J.J. Thomson, Rutherford started or developed interest in finding out or trying to explain what makes up the atoms. So later on, after the Rutherford alpha particle scattering experiment, the idea that atoms are made up of three types of particles, these were the protons, neutrons, and electrons, was suggested as we explained in the nuclear model. And this seemed to simplify things even more. And scientists were very, very happy with it since it seemed to provide a very simple explanation of a complex world. So after the Rutherford alpha particle scattering experiment, an atom was found to be or was considered to be made up of three particles. These were the protons, neutrons, and the electrons. And this idea was so much welcomed by the chemists. The protons, neutrons, and electrons were thought to be actually the fundamental particles at that time. Unfortunately, later on, it was further found that the protons and electrons, which the protons, electrons were the protons and neutrons were further found to be divided into other smaller particles that we are going to call quarks at a later time. So later on, it was found that protons, neutrons, and electrons, which were expected to be fundamental particles, or which were expected to be the smallest particles, we later on found that not all of them would be considered fundamental particles because the electrons, even though they were not subdivided further, scientists were able to subdivide protons and neutrons into something simpler. The protons and neutrons, of course, must have been kept together by a strong nuclear force which glued them together inside the nucleus. Later on, physicists discovered many other particles by looking at the cosmic rays which arrive on Earth from space. These were actually believed to be remains of the Big Bang theory, and these cosmic rays carried particles which did not fit any of the patterns that had already been discovered earlier on. So the cosmic rays did not fit patterns of protons, electrons, or neutrons. So the scientists gave them names such as pions, kaons, muons, etc., using up most of the letters of the Greek alphabet. And the discovery of new particles with masses different from those of protons, neutrons, and electrons suggested to scientists that not all protons, neutrons, and electrons could be considered to be fundamental particles. And that's why later on the protons and neutrons were found not to be fundamental particles, because scientists proved and verified that the protons and neutrons were further formed, or were further consisting of smaller particles which scientists called quarks. So after the discovery of antimatter in cosmic rays, we remember we said antiparticles have the same mass as the normal particle, but they had opposite charges. So therefore, this led to the theory that there exists antimatter. And after the discovery of antimatter in cosmic rays, then the quantum theory that all fundamental particles have corresponding antimatter particles was developed. Therefore, the matter and the antimatter particles must be coexisting, and the matter and antimatter particles are believed to have the same mass but opposite charge. This theory was to be supported by particles such as the antineutron, the antiproton, and the antielectron. So today as we speak, we can now believe that we started with the matter as a whole, as the ancient Greek proposed, being made up of smaller particles that were called atoms. And at that time, 2000 years ago, the atoms were the smallest. Later on, after the Rutherford alpha particle scattering experiment, it was found that the atoms were further broken down into protons, neutrons, and electrons. And from that time, therefore, the atoms were no longer the smallest, but the protons, neutrons, and electrons were considered to be the smallest. Later on, after the quantum theory was proposed and after observation of cosmic rays, which were believed to be remains of the Big Bang, it was later on found that protons and neutrons were formed or were composed of smaller particles that we today call quarks. So protons and neutrons were no longer fundamental, or they were no longer the smallest particles, because they were made up of something smaller. So today it is believed that the electrons, because the electrons, scientists have failed to break down the electrons. So today it is believed that the electrons, together with the quarks, might be the smallest particles that make up matter. So what I'm saying is the fundamental particles, these include the quarks, which are believed to combine to form smaller particles that are called the protons and the neutrons. The protons and neutrons were found to be made up of quarks, and the neutrons, therefore, combined together with the protons, the neutrons combined with the protons and the electrons to form what we call the atoms. So breaking down the atoms, we obtain protons, neutrons, and electrons. So it is these atoms, therefore, that make up matter. So matter can be traced backwards as being made up of atoms, which atoms are made up of protons, neutrons, and electrons, which protons and neutrons are made up of quarks and electrons. So it is like it is only the quarks and the electrons which have not yet been broken down any further. So can we say the quarks and the protons, the quarks and electrons are the smallest particles? So what are fundamental particles therefore? So since we cannot break down quarks any further, they are the simplest we can have. Since we have not broken down electrons any further, it is the simplest we can have. So the smallest particles from which we start until we arrive at matter could be called the fundamental particles. So quarks and electrons are going to be called fundamental particles. So what are fundamental particles? So to define fundamental particles, these are fundamental particles are those particles that could not be subdivided any further. They are the simplest that we can have. Fundamental particles are not made up of any other simpler particles. They are the simplest themselves that we can have. That's why we call them fundamental. The same way we can say a foundation of a house is the fundamental. It is the building block. It is the starting point. Those are fundamental. So we have mentioned that protons and neutrons were found not to be fundamental anymore because they are composed of yet smaller particles that were later on called the quarks. So protons and neutrons were broken down any further, and therefore they were called non-fundamental particles because they were made up of quarks. But quarks themselves have not been broken down, and therefore quarks can be considered to be fundamental particles. After the discovering of antimatter, that is matter but with opposite sign of charge as normal matter, in cosmic rays, then the quantum theory that all fundamental particles have corresponding antimatter particles was developed. That matter and antimatter particles have the same mass but opposite charge. So if we have matter, then we have a particle. If we have antimatter, then we should be having an antiparticle. And this theory was supported by observation of particles such as the antiproton, which was found to have the same mass as the normal proton, but with the opposite charge. Then the antineutrino. Of course, the antineutrino, we cannot talk about charge when we are referring to antineutrino, but the discovery of the antiproton and antielectron led to an extrapolation that if antimatter, antiparticles, antiprotons exist and antielectrons exist, then there should be an antineutrino, even though the neutrino has no charge. I want you to notice that any antiparticles, we are always going to put a bar on top of the letter which corresponds to the normal particle to mean antiparticle. For example, if a proton is written as P, the antiproton will be written as P with a bar on top. If a neutron is written as N, the antineutron is written as N with a bar on top. So that means the quantum theory that all fundamental particles have corresponding antimatter particles was to be adopted at this point. So today as I speak, it is actually the quarks. Today it's the quarks, the leptons, and when I talk about the quarks, those are the particles which make up the protons and neutrons, as we shall see later on, the leptons. And when I talk about leptons, we shall talk about these are going to be the electron, the positron, which is the negative electron, and the neutrino, and their corresponding antimatter particles. For example, the antimatter particle or the antiparticle of the electron is the antiparticle of the electron is the antielectron, which is the positron. And of course, the antiparticle of the neutrino is the antineutrino. These ones are going to be called fundamental particles. So it is the quarks and leptons, which are the smallest, that have not yet been broken down any further. Therefore, we call them fundamental particles. Okay, so let's look at the family of particles. So having seen that matter is broken down into atoms, which atoms are broken down into protons, electrons, and neutrons, which protons and neutrons are broken down into quarks. Then we can now classify particles into two major families. Of course, particles are going to be classified into two major families. We have the ones which are made up of quarks and the ones which are not made up of quarks. The particles which are made up of quarks are going to be called the hadrons. And we mentioned that protons and neutrons are made up of quarks. So it means protons and neutrons are going to entirely be hadrons. But hadrons are also going to be classified into two, as we shall see later on. There are those hadrons which are made up of three quarks, and there are those hadrons which are made up of a quark and an antiquark, because the quantum theory or the quantum theory that particles or that matter has its corresponding antimatter, or the quantum theory that the quantum theory that antiparticles or particles have corresponding antiparticles must be obeyed. So if we have quarks, we should also be having corresponding antiquarks. So there are those particles which are made up of quarks and antiquarks. We shall later on call them mesons. Then there are those particles which are made up of only three quarks. We shall call them baryons. So hadrons can either be baryons or they can be mesons. For baryons, they are made up of three quarks. So three quarks combined form baryons. And for mesons, they are made up of a quark and an antiquark. So one quark and one antiquark combine to form what we call mesons. So hadrons are made up of quarks or antiquarks, and baryons are made up of three quarks. Mesons are made up of a quark plus an antiquark. Of course, an example of baryons, particles which are made up of three quarks, are the protons and the neutrons. And then there are those particles which are made up of a quark and an antiquark, which we call the mesons, and these are the pions and the kaons. But on the other side is a family of particles which are not made up of quarks, and we call them leptons. Remember I said the leptons, together with the quarks, form what we call the fundamental particles. Okay, so we start with protons and neutrons. These are made up of three quarks, and any particles which are made up of three quarks are called baryons. So the baryons, we have also pions and kaons. These are made up of a quark and an antiquark. Particles which are made up of a quark and an antiquark are called mesons. Of course, together the baryons, together with the mesons, form what we call the hadrons. These ones, baryons and mesons, are made up of quarks or call them antiquarks. That's why we call them hadrons. Hadrons are those particles made up of quarks or antiquarks. They can be the baryons or the mesons. So these ones, the baryons and the hadrons the baryons and the mesons form what we call the hadrons. But on the other side, we have particles such as the electron and its corresponding anti-electron, which is the positron. We have the neutrino or the antineutrino and its corresponding antiparticle, which is the antineutrino, electron neutrino and electron antineutrino. These ones combine to form what we call leptons. So the leptons and the hadrons are the two families of particles. So particles have two families. We have the hadrons and the leptons. The hadrons are made up of three quarks. The hadrons are made up of three quarks. They are made up of quarks. The leptons are not made up of any other particle. They are not made up of quarks. The leptons include the electron, the anti-electron, the neutrino, and the antineutrino. The hadrons are the baryons and the mesons. The baryons are made up of quarks, and the mesons are made up of quarks and antiquarks. For baryons, to be specific, those are three quarks. And for the mesons, it is a quark, one quark, and an antiquark. Examples of baryons, we have the protons and the neutrons. Examples of the mesons, we have the pions and the kaons. Okay, so a few things we need to note from here. Hadrons are all particles affected by the strong nuclear force, and I've said they are made up of quarks or antiquarks. That should not be forgotten, quarks or antiquarks. They are made up of quarks or antiquarks. The word hadron comes from a Greek word which means bulky in mass. bulky. Think of the electron. Think of the proton, for example. The proton is a hadron. The mass is about 1.67 times 10 to the power of minus 27 kilograms. This is the bulk. This is heavy at nuclear level or at atomic level. This is heavy compared to the mass of the electron. The mass of the electron is much smaller than the mass of the proton. So the word hadron comes from a Greek word which means bulky in mass. So at smaller levels, the protons and neutrons are the most bulky particles. Then on the other hand, we have the leptons. These are particles that are not affected by the strong nuclear force. They don't need anything to glue them. The strong nuclear force does one role, it glues particles together. That's why the hadrons interact, the particles which make up the hadrons, or the particles we call the hadrons, interact via the strong nuclear force because they may have the same charge, and instead of repelling each other, they are glued together, they stick together due to the strong nuclear force. So the leptons, for them, they are not affected by the strong nuclear force. They are not made up of any quarks. They are just believed to be fundamental particles. And the word lepton comes from the Greek word which means light in mass. So this means, therefore, that the protons and the neutrons are bulky, they are heavy compared to the electrons or the leptons. Remember, the mass of the electron is 9.11 times 10 to the power of minus 31 in kilograms. So the mass, the electrons are lighter in mass. So let's go inside the hadron. What is inside the hadron? Now, this is going to be what we call the quark mode of the atom. Although the atom was believed to be made up of just protons, neutrons, and electrons revolving around the nucleus, the nuclear model did not mind about what is inside the protons and what is inside the neutrons. This was the concern of the quark model, describing what is inside or what makes up the protons and the neutrons. So inside the protons and neutrons, we have particles which we call the quarks. And these ones are considered to be the fundamental particles that make up hadrons. So the quarks are the fundamental particles which combine either in three to make the baryons, or a quark and an antiquark to make the meson. So these ones are the fundamental particles which combine to form the hadrons. The quarks, by the way, do not exist in isolation. They always exist in groups, either in groups of three to form a baryon, or a quark combining with an antiquark to form a meson. No single quark has ever been found in isolation. They are always found in groups of three to form baryons, or a quark and an antiquark to form what we call a meson. So the quarks exist in types which we shall call flavors. The types of quarks are called flavors of quarks are going to be 6 types. We have what we call up, down, charm, strange, top, and bottom. These are quarks, these are called flavors of quarks or types of quarks. Now someone will say, why are they called up, down, top, bottom, and so on and so forth? These words do not hold their English meaning. The same way you can be called patience when you're not patient, but just to identify you. So these words do not carry their English meaning. They were words which were used by scientists to just distinguish the different quarks or the different flavors that make up these fundamental particles. What is special about the quarks and all the property of quarks is that they have charges which are fractions of the electron charge. Remember, the electron charge or the elementary charge is E. So the quarks are believed to have charges which are a fraction of E. Because if a proton has a charge of positive E, that means the quarks which make it up, because there are 3 quarks, the charge of each quark must be a fraction of E, so that when we sum up, we get E. So the quarks have an odd property that their charge is a fraction of the elementary charge, or is a fraction of the electron charge. So those are called the quarks. They are fundamental particles which make up the fundamental particles which make up hadrons or baryons and mesons. So in summary, let's summarize the types of quarks. Like I said, there are 6 flavors or types of quarks. So we shall talk about the quark flavor, which is the type, the corresponding symbol, how we shall represent that quark, its charge. Remember the quantum theory, whenever we have a particle, we have its corresponding antiparticle. So if we have a quark, we expect to have a corresponding antiquark. So we should know the symbol of a quark. And remember, a particle and its corresponding particle are believed to have the same mass, but simply opposite charge. So if we know the charge of a quark, the charge of the antiquark is just going to be the opposite. So to begin with, let's start with an up quark, the up flavor. We shall use letter U, small letter U for the up flavor. Of course, the charge is positive 2 over 3e. You need to note those charges. And if we consider its antiquark, it is going to be called anti-up or anti-up quark. And we shall put a bar on up, and the charge is going to be minus. Then we talk about down. Down we represent it with letter D, small d. The charge is minus a third E, a fraction of the elementary charge. Then the antiquark is going to be anti-down. The symbol we shall write D with a bar on top. The charge is positive, opposite charge. Talk about charm. Charm is going to have the charge of positive 2 over 3e. Then the antiquark is going to be anti-charm. The charge we shall put a bar on top of C. The charge, that is the symbol for anti-charge. Then anti-charm, and the charge is going to be minus 2 over 3e. Then we shall talk about strange. The quark flavor strange is represented by letter S. That means the anti-quark and strange is going to be S with a bar on top. The charge of strange is going to be minus 1 over 3e, and the charge of anti-strange is positive 1 over 3e. Then we have top. Top is represented with the small letter t. The charge is plus 2 over 3e, and anti-top is going to be with t with a bar on top. The charge is going to be negative 2 over 3e. And finally, we have bottom, which is going to be a b minus 1 over 3e charge. Anti-bottom with b with a bar on top. And then the charge of anti-bottom is plus 1 over 3e. Now, you will notice a simple pattern here. If you are very observant, I want you to notice a simple pattern here. To be up, I think that is a good word. Something charming is a good thing, and being on top of everything is also a good thing. And look at the good words correspond to charge of positive 2 over 3e. Up, charm, top. So there are only 2 charges which we are considering here, plus 2 over 3e and minus 1 over 3e. So if the word is good or pleasing, the charge is plus 2 over 3e. If the word is negative, putting someone down, something strange, being at the bottom, those are negative words. The charge is minus 1 over 3e. So of course, when we look at the antiparticles, we just change the signs. Up, being up, I think, is a good thing. Being charming is a good thing. Being on top is a good thing. Being on top of everything, top of class, top of the game, Everything related to something good, the charge is positive 2 over 3e. And the other one is negative 1 over 3e. For the antiquarks, we just change the sign. So you must master, or you must be aware of these charges, and they should become part of you, because you'll use them several times in calculations, in exams, and so on and so forth. Okay, so let's discuss the quark structure of these particles, some of these particles. Which quarks make up the protons? Remember, we said quarks combine to form either protons or neutrons, which we call the baryons. Or quarks combine in such a way that a quark combines with an antiquark to form what we call pions, or kaons, what we call mesons. So This is the quark composition of some of the common particles. The proton. A proton is found to have a up, down. It has two up quarks and one down quark. Remember, the charge of up is positive 2 over 3e. The charge of down is negative 1 over 3e. So what is the total charge? We have two up quarks, so I multiply this by 2. Then I add this to negative 1 over 3. So that means our total charge here is going to be positive E. A neutron is made up of up, down, down. Then of course the antiproton is just the opposite of the proton. So we put bars on each of these antiparticles. So antiproton is going to be ant up, ant down. And antineutron is going to be ant up, ant down, ant down. So proton, two up quarks, one down quark. Neutron, one up quark, two down quarks. Antiproton, two ant up and one ant down. Antineutron, one ant up and two ant down quarks. So for charge, because each up quark has positive 2 over 3e, we just sum up all these charges, and the charge of a proton is going to be positive E, as we already knew. Of course, in our minds, we know that the charge of a neutron is 0. So if we consider quarks, it has one up quark, so that is positive 2 over 3e, plus two down quarks, so that is plus negative 1 over 3e plus negative 1 over 3e. When you sum up, that gives us 0 as the charge of a neutron. The antiproton, ant up, we just get the opposite of positive 2 over 3e, which is minus 2 over 3e plus minus 2 over 3e. Then ant down, because down has minus 1 over 3e, ant down is going to be plus 1 over 3e. And when you sum up, you will get negative E or negative 1e as the charge of the antiproton. Then of course the antineutron will still have no charge, but the ant up has minus 2 over 3e, ant down is plus 1 over 3e, ant down plus 1 over 3e. And when you sum up, I think that gives us automatically 0. Okay, so what should we note therefore? A few things we need to note here. Normally, the antiproton and antineutron are going to be called these ones may be always called antibaryons. Instead of just calling them baryons, we shall sometimes call them antibaryons, but they are still baryons anyway. And they are still hadrons anyway, because they are made up of quarks or antiquarks, whatever. So the antiproton and antineutron are sometimes going to be called antibaryons. Remember in beta decay we said sometimes a proton decays into a neutron and a neutron decays into a proton. So when a proton decays, a neutron is formed. So the quark flavors change. If we have a proton, it is becoming a neutron. So what has happened? It's like up, down is becoming up, down, down. So we say the quark flavor changes. When a proton decays, a neutron is formed. So the quark flavor changes. That is, and by the way, when a neutron decays to a proton is formed. When a neutron changes to a proton, also the quark flavor changes. That is, we know that a neutron is up, down, down. Now it changes to up, down. So it's like one down quark changes to an up quark. As for a proton to a neutron, one up quark changes to a down quark. So in both cases, when a proton changes to a neutron, that is during beta decay, when a neutron changes to a proton, that is during beta decay, the quark flavors change. So how do they change? So for a proton to a neutron, up changes to up, down becomes up, down, down. That one we have noticed. And for a neutron to a proton, up, down, down changes to up, down. Also note that in strong interactions, the quark flavor is conserved. So every time interactions take place, the quark flavor is always going to be conserved. In other words, the quark flavor must remain the same. Okay, so that was the quark flavor of what we call baryons. Let's discuss the quark flavor of mesons. The quark flavor of mesons. The quark structure of mesons. Remember I said mesons, these are particles which are made up of a quark and an antiquark. So these are considered to be intermediate particles which are made up of quark antiquark pairs. By the way, mesons are supposed to be intermediate particles of other particles, but we shall not go into the details of that. But what we know is that they are made up of quarks and antiquarks. It is a quark-antiquark pair. So a meson is made up of one quark and one antiquark, as we described earlier on. Note that the quark and antiquark can be of totally different flavors. It can be up and down. It can be strange and up. Totally different flavors. The most common mesons fall into two categories that we shall talk about. We have what we call the pions or the pi mesons, normally written as pi like this. And the other ones are called the kaons or the K mesons. These are going to be the most common quark flavors. I mean the most common mesons in everyday science, which are always mentioned. So the mesons fall into two categories, the pions and the kaons. What is the difference between the pions and the kaons? Let's discuss the structures in detail. So we shall talk about the pions, the quark composition, and the charge of the pions. So the pions are made up of up and down. You don't need to remember the pions, the quark composition of the pions, but this is just for learning purposes. Remember the charge of up is plus 2 over 3e, and down is plus 1 over 3e, so the total charge of the pi plus is plus e. That's why it is even called pi plus or pi mesons. Then we have pi minus or pi minus meson, which is anti-up and down. Remember, anti-up has a charge of negative 2 over 3e, and down has a charge of minus 1 over 3e. So when we sum up, we get total of minus e. So that is total charge. That's why it is called pi minus. We also have what we call pi zero. Pi zero, which means the charge is zero. So we can have up and anti-up, which will be positive 2 over 3e plus negative 1 over 3, which automatically gives us 0. Or we have down, which is minus 1 over 3e plus positive 1 over 3e, which also gives us 0. So the charge of pi 0 is automatically going to be 0. It is either up and up, down and down. Now you may ask, why can't it be strange and unstrange? Strange and unstrange. So pions are made up of a combination of either up, down, in any combination, or corresponding antiparticles without a strange in this case. So that's why we call them pions. For pions, they are made up of up, down, or up and down with those corresponding combination up and down, and up, down, up and up, down and down. There's no strange for pions. And what distinguishes pions from kaons is because kaons must always hold a strange on them. So let's see the kaons. So for the kaons, they always have a strange. So for the kaons, like I've said, they always have a strange. They always have at least one strange. That's what distinguishes them from the pions. For the pions, a pion consists of an up or down quark and an antiquark. That is a pion. But for a kaon meson consists of one up or down quark or antiquark and always one strange or unstrange. There must be always a strange or unstrange. That is the rule. So for a kaon, there is always a strange or unstrange in combination with up, down, or anti-up or anti-down. Those are the strange. Those are the counts. So we have the K plus, where the charge should be plus. So we have up, it has up and strange. So when you add up the charge plus 2 over 3e plus 1 over 3, remember the charge of strange is minus 1 over 3e. So if it is anti-strange, it becomes plus. So that is positive e as the charge. We also have K minus, which is ant up and then strange. So ant up is negative 2 over 3e, then strange is 1 over 3e minus. So this gives us negative e. We also have K0. We also have K0. K0 has the common quark composition of K0 is down and ant strange. Now someone will ask, why can't we have strange and ant strange? But the common K0 or count 0 is going to be down and strange. And of course the charge is 0. When it is strange and strange, it is going to be given a specific name which is not K0, but it is going to be called a phi. It is going to be called a phi meson. Okay. So these ones are the counts, and what is special about the counts is that they always carry a strange. For the pions, they don't carry a strange or unstrange. For the counts, they carry a strange or unstrange always. That's what distinguishes them from the pions. A few things we again need to note here. I've not put strange or unstrange even when it gives us a charge of 0 for the K0. So there also exists phi, the phi meson, and is made up of a strange quark and an unstrange quark. So the phi meson has a quark composition of strange and unstrange. So the antiquarks, by the way, are needed to account for the existence of antimatter. The only way we can explain the existence of antimatter is if we can believe that antimatter is made up of antiparticles, where antiparticles are made up of antiquarks, forming what we shall later on call antibaryons. Okay, so the protons and the neutrons were called the baryons, and the antiprotons and the anti-electrons can always be called antibaryons. So the baryons, as we mentioned earlier on, or as we saw earlier on, the baryons were made up of 3 quarks. The baryons were made up of 3 quarks. And the antibaryons would be made up of maybe 3 antiquarks. So the protons and the neutrons were baryons because they were made up of basically 3 quarks. And now the mesons we have called them, the mesons are made up of quarks, and we have called them, the mesons were made up of a quark and an antiquark. We don't have something like antimeson, we don't have antimesons, but we have antibaryons. We have antibaryons because antibaryons are believed to be made up of antiquarks, such as the antiprotons and antiprotons and the antineutron. So antimatter is made up of antiparticles, and antiparticles are most likely going to be made up of antiquarks. But we noticed that whenever a particle meets its corresponding antiparticle, what happens is that they annihilate. To annihilate is like to come together, where their masses become energy in form of photons or gamma photons. We shall talk about annihilation in more details under the PET scan or the positron emission tomography scan. So let's now talk about the leptons. Leptons. We said leptons together with quarks form what we call fundamental particles. So we said leptons are those particles which are not affected by the strong nuclear force. They are the light particles. I said leptons comes from a Greek word which means light in mass. The leptons include the electron, as we mentioned, the neutrino, and their antimatter particles. The antimatter for the electron is the positron. The antimatter for the neutrino is the antineutrino. Of course, there also exists other leptons we don't mention, like the muons, and so on and so forth. But in exams, you already mention electrons, the neutrino, positron, and the antineutrino. Or you'll talk about the anti-electron, the electron neutrino, and the electron antineutrino. We have mentioned the neutrino and antineutrino previously in beta decay. So those are the leptons. These particles are not affected by the strong nuclear force. They are not broken any further, so these particles do not appear to be composed of any smaller particles and are therefore considered to be truly fundamental particles. So what makes leptons fundamental is because they have not been broken down any further. They are the simplest. Therefore, leptons are called truly fundamental particles because they cannot be broken down into anything simpler, anything smaller. They are the smallest we can think about at that level. So leptons are fundamental particles together with quarks. Leptons are fundamental particles together with quarks. So we talked about beta decay under beta, alpha, beta, and gamma radiations in lesson 1. So it is now high time for us to understand in more details beta decay. Having understood the quark composition or the quark mode of the atom, let's now understand beta decay. So number 1, you should recall that during the decay of a neutron or during the decay of a neutron in the nucleus, a proton is formed. During the decay of a nucleus, a proton is formed, and an electron and antineutrino were emitted. Remember, the antineutrino are explained as the antineutrino accompanied or the antineutrino accounted for the variation in energy when beta emission or beta decay takes place. In terms of quarks for this reaction, a neutron is changing or decaying into a proton. In terms of quarks, we have that up, down, down is changing to up, down. So the quark flavor is not conserved as the down quark has changed to an up quark. The reaction cannot be due to the strong force because if it is for the strong interaction, for the strong nuclear force, the quark flavor must be conserved. The quark flavor must be the same on both sides of the equation. But because the quark flavor has changed, one down quark has become an up quark when a neutron changes to a proton. So it means this reaction or beta decay, the force response for the beta decay is no longer the strong nuclear force. Another force should account for the beta decay, and this is called the weak nuclear interaction force. The weak nuclear interaction force is the force responsible for a proton inside the nucleus changing into a proton for the neutron inside the nucleus changing into a proton, or the proton inside the nucleus changing into a neutron. So the strong nuclear force cannot account for a neutron changing into a proton because for a strong nuclear interaction, the quark flavor must be conserved. But since it is not conserved, we have lost one down quark and gained one up quark. That means the stronger force is not responsible for this. Another force must be responsible, and there are only two forces at nuclear level, which is the weak and the strong. So the weak nuclear interaction is now responsible. So we use the word interaction because we're dealing with smaller particles. Since they are smaller particles, the word force does not really make any good sense. That's why we use interaction instead of force. So the weak nuclear interaction is the force responsible for this decay or for beta decay. So we say that the weak nuclear force is the force responsible for beta decay. Why is it called weak? It is called weak because it only operates within a very short range. So it is a short range distance. The particles must come very, very close for this force to have effect. That's why we call it the weak nuclear force. It acts in a very, very short or very, very tiny range, very short distance. The particles must come close enough for a neutron for them to exchange their quarks. so that what was a neutron becomes a proton. So when particles come so close, the weak force may cause the quark flavors to change, resulting in the change of the properties of the entire element. Because the quark flavors have changed, they have rearranged themselves, the particle inside a neutron has become a proton. We now have one more proton. It is now a new element. It will even behave differently. We now have a new atom, which therefore makes the element to be different and to behave differently. However, I want you to also observe that the total lepton number before a reaction must be equal to the total lepton number after the reaction. For example, we have a neutron, 1, 0, has changed to a proton, 1, 1, plus E0, negative 1, plus. This is accompanied by an antineutrino or an anti-electron neutrino. So we have up, up, down, up, up, down, down, and up, down. So here we have 0 lepton number on the left-hand side. On the right-hand side, we have 1 lepton. Because this is, we have 0, this is a proton is not a lepton, so that is a 0 proton. This is a lepton, but is an electron. This is not, this is a lepton. So this is a negative particle, which means the lepton number of a negative particle is negative 1. This is an electron, its lepton number is 1. This is an anti-electron, an antineutrino, its lepton number is negative 1. So for a lepton number is 1. For the anti-lepton, lepton number is negative 1. So it means total lepton number is still 0 on the right-hand side. On the left, there is no lepton number is 0. On the right, the electron is a lepton number is 1. The antineutrino is an anti-lepton number is going to be negative 1. So the total lepton number is conserved. So in such reactions, the lepton number is always going to be conserved. Okay. I want you to also note that in the above beta minus decay, the total lepton number before reaction was 0. That is, on the left, lepton was 0. The lepton number for the electron particle is positive 1, and for the antiparticle is negative 1, giving a total of 0 on the right-hand side too. So the lepton number is further conserved. So in a nutshell, in this part of leptons, we have considered leptons as being fundamental particles. That's number 1. Number 2, they are not affected by the strong nuclear force, but they interact via the weak nuclear force or the weak nuclear interaction. Number 3, we have noted that the weak nuclear interaction is responsible for beta decay. Number 4, we have also noticed that a proton may change into a neutron. And if a proton changes into a neutron or a neutron changes into a proton, the quark flavors change. But the lepton number is going to remain constant. So we were trying to understand beta decay. How do we come up with beta decay? Because the quarks, which make up protons and neutrons, may come very close. The weak nuclear interaction comes into play, and then there will be exchange of quarks, resulting into a proton changing into a neutron or a neutron changing into a proton. Of course, this is normally accompanied by either a neutrino or the antineutrino, and that's why we said the energy emitted or the energy is not going to be discrete whenever beta decay takes place. Okay, I've given a further example here. Describe the reaction where a proton in the nucleus turns into a neutron and emits beta particle in terms of the quark model. So in terms of the quark model, it means we shall eliminate all the particles and only explain this in terms of quarks. So in our solution, a proton is changing into a neutron. Of course, this is accompanied by a beta plus. E0 positive 1, that is a beta plus particle. An antiparticle must be accompanied by a neutrino. This is called the electron neutrino. Because beta plus a positron is an antiparticle, it cannot again be accompanied by an antineutrino. It must be accompanied by a neutrino. So we know that a proton has up, up, down, and a neutron has up, down, down quark. So it's like up, up, down changes to up, down, down. So an up quark changes into a down quark. So they said we should explain this in terms of only fundamental particles. So in terms of fundamental particles, this is the equation we are looking for. For a neutron, if a proton is up, up, down, it changes to up, down, down. This is accompanied by a positron or beta plus. This is, by the way, the same as beta plus, which is 0 plus 1. Then accompanied by an electron neutrino. I said this can also be written like this, electron neutrino, something like that. Or they can even put zeros here, electron neutrino. So that is in terms of fundamental particles. We only have quarks, leptons, quarks, those are fundamental. The positron is a fundamental particle. The neutrino is also a fundamental particle. Okay. So I have a self-check. I think I'll give a hint where possible. Use the equation in the example above to explain why the neutrino can have no charge and very little mass. Why will the neutrino have no charge? So we saw that a proton change into a neutron accompanied by beta a positron, which is 0, 1, plus the neutrino. So the neutron is 1, 0, proton is 1, 1. So use the equation in the example above to explain why the neutrino can have no charge and very little mass. Or it will not also have mass. So of course, for every nuclear reaction to take place, the charge must be conserved. Since the positron already has a charge of positive 1, then the neutrino cannot really have any charge. And of course, the nucleon number must be conserved, so the neutrino cannot really have charge. What is the difference between a hadron and a lepton? So we have said a hadron is made up of quarks, and the lepton is not made up of any quark. So this one, no quarks. We also know that the lepton is fundamental. A hadron is not fundamental because it's made up of quarks, not fundamental. What are the differences between a proton, positron, and a photon? So a proton, this one is a hadron. A positron, this one is a lepton. A proton is made up of 3 quarks, so it is a hadron. A positron is a lepton. A positron is actually an anti-electron. And then a photon, which you will see in paper form, a photon is just energy of electromagnetic radiation. A photon is a packet of energy of electromagnetic radiation. So a photon is just energy. When we say gamma photon, that is just energy of electromagnetic radiation. So that is the difference between those three. Okay. Show that the phi meson is neutral. Of course, this one is easy. Phi meson is strange, is made up of strange and unstrange. So the charge of phi strange, we know that strange has a charge of minus 1 over 3e, and strange is therefore going to have a charge of plus 1 over 3e. So the charge is going to be minus 1 over 3e plus 1 over 3e, which is equal to 0, so it is neutral. Write down the quark composition of the following and deduce their charge. So we have helium. So helium has 2 protons plus 4 minus 2, it has 2 neutrons. Okay, so the quarks, we have 2 into up, up, down for 2 protons. We also have 2 into up, down, down for neutrons. So I'm going to collect like terms. So this is the same as 2 up, up becomes 4 up. So that is 4 up and 2 down, plus we have 2 up and 4 down, which simplifies to 4 up plus 4 up becomes 6 up, and 2 down plus 6 down becomes 6 down. So the quark composition of helium is going to be 6 up and 6 down. How about the charge? The charge, I'll write the charge here. So the charge is going to be 6 times up is 2 over 3e plus 6 times down is negative 1 over 3e. So 6 times, sorry, this is going to be 4e. So this is 4e minus 6 over, that is minus 2e, which gives us a charge of positive 2 times e. So the charge is positive 2e. Then lithium, you can try to check lithium, but of course the charge of lithium is going to be positive 3e. The quark composition is going to be 6, 3 up, which is 3 into up, up, down, plus 7 minus 3, that is 4. 4 neutrons, that is 4 into up, down, down. So I have 3 times 2, that is 6, plus 4, that is 10. 10 up. 3 down plus 4 times 2 down, that is 8 down, plus 3, that is going to be 11 down. That is the quark composition, 10 up, 11 down. And then for the charge, I will just simply say 10 down, 10 up, which is 10 times 2 over 3e, plus 11 down, which is 11 times negative 1 over 3e, which I'm very sure will give you positive 3e. Of course, we know that the number of protons is the charge of the nucleus. Sodium 2411, magnesium 2412, plus X plus gamma radiation energy. Identify X. So this is gamma radiation, so it doesn't affect the proton and nucleon number. Because this is 11 and this is 12, to balance, I should put here negative 1. And the nucleon number has not changed, so this is 0. So X is going to be an electron. It is an electron, or you can call it beta minus. When I just say electron, I mean beta minus. Whenever they just say electron, they're referring to beta minus. If they want beta plus, they will be specific and say beta plus. Show whether the following reaction can occur. Of course, if it can occur, the lepton number must be conserved. So we have on the right-hand side, the lepton number here is 0 because we have a proton and a proton, those are not leptons. On the right-hand side, the lepton number is 0. On the left-hand side, the lepton number is 0. So that's number 1. Number 2, we can consider the baryon number. On the left-hand side, the baryon number is 2. 1, 2. These are baryons. So this is 2 baryon number. On the right-hand side, baryon number, this is 1 baryon. This is negative 1 because the antiparticle has baryon number negative. This is a baryon. So the baryon number is, on the left it is 2, on the right it is 1. So the baryon number is not conserved, so the reaction does not occur. It doesn't occur because baryon number is not conserved. The baryon number not conserved. So that reaction will not occur. Lastly, so we have a reaction which has been an equation which has been represented as shown here. So let's see the question. Identify the values of A, B, identify the radiations D, E, F, G, and H, identify the isotopes. So let's start with A and B. So when you look at this and this, so this is beta, this is beta. They say this is beta, so we want to find A and B. So if it is beta, we have only two options. A must be 0. I mean A, because it is beta, this is 0. We don't know whether it is bit 0 plus 1 or 0 minus 1. But this is 0. So that means A should be 214. A should be equal to 214. Because whether it is beta 0, beta plus, or beta minus, A will not be affected. So A is 214. And if A is 214, yet from here to here, this reduces by 4, then, and this one is 2, then this is, G is going to be an alpha particle. So this is going to be alpha 4, 2. So this is going to be alpha 4, 2. So if this is alpha 4, 2, I will add backwards 210 plus 4, and then I'll add 82 plus 2. 82 plus 2, which gives us 84. So B is going to be 84. B is going to be 84. Because so if B is 84, so this is going to be 0 plus 1. So A is 214, B is 84, because from A, because A is 214 and it has reduced by 4, so it is going to give us an alpha particle, alpha 42. The nucleon number reduces by 2, proton number has reduced by 2. So B is going to be 84. Then identify the radiations D, E, F, G, and H. So what is D? D, proton number is reduced by 2, nucleon number is reduced by 4, so D is alpha. This is alpha, alpha 42. E, proton number is reduced by 2, nucleon number is reduced by 4, so this one is also is going to be alpha. It is emitting alpha. F, proton number has increased by 1, nucleon number has not changed. So proton number increased by 1. So this is going to be beta 0, negative 1. So that when I say 82 minus negative 1, it gives me 83. So G is going to be beta minus. Then that is F. Then G. G is automatically an alpha particle. That one is alpha. G is alpha. Then H. H, proton number has not changed. Nucleon number has not changed. So H is going to be gamma. No change in proton number, no change in nucleon number. That is gamma. Identify the isotopes. So isotopes have the same proton number, different nucleon number. So same proton number, we have Pb 21482. We have Pb 21082. I think those are the isotopes. We also have, I think we have another one, because B was 84. So we have PO 21884 and PO 214 and 84. So we have this one here and this one here. These are isotopes. They have the same proton number but different nucleon number. This one, same proton number but different nucleon number. So those are the isotopes. For more understanding, make sure you watch the solved past paper questions. They will give you the best idea of what the examiner is looking for. Until next time, bye-bye.